For our last statistical test, we're going to look at what's called a chi-square goodness of fit. There are two chi-square tests. This one is goodness of fit. The primary information that makes it a goodness of fit chi-square is that you're looking at proportions, sometimes known as percentages. And you're looking at those between your rows of observed information from a sample to what you should be expecting based on the chi-square formula. Those rows are going to be the second part that makes something a chi-square, that they are categories. Whether nominal, as in names with no order, or ordinal pieces of data, where there's some order, but there's definitely no numbers. And with any statistical test, we're looking for the inferences from a sample to a population that are statistically significant. Let's try one. A researcher for an automobile manufacturer wishes to see if the ages of automobiles are equally distributed among three categories: less than 3 years, 3 to 7 years, and 8 years and older. A sample of 30 adult automobile owners is selected. At alpha equals 0.05, can it be considered that the ages of the automobiles are equally distributed? In other words, are the proportions equal among the three categories? In order to answer the question, we need hypotheses. In HO, we're saying yes, the proportions are all equal for the automobile age. Then our H1 would be the proportions are not equal. Our critical values are determined by, first of all, alpha. In this case, alpha is 0.05. When calculating this by hand, I also need to know the degrees of freedom. It's going to be one less. As in our example for t-testing, someone doesn't have a choice. So I take my number of rows and I'm going to subtract 1. So my degrees of freedom are 3 minus 1, or 2. This is going to give me a critical value based on the chart that I'm going to read. So I read 2 degrees of freedom and 0.05. So my chi-square is 5.991. Now I need the calculated value. In order to come up with the calculated value, I need what's called my expected value. That is, if I take all of my 30 people and divide that between my three categories, if they were equally distributed, they should each have 10. So 10 is my expected frequency. We'll call it E. My calculations are done as follows. The formula for chi-square is this. We're going to do the summation of the observed values minus the expected values. That difference is squared. Then it's divided by the expected value and then added together. The observed was 8, the expected was 10. Divide, after you square them, by the expected value. The second value was 10. Its expected value was 10. Subtract and square. Divide by the expected value. Then we take the third, which was 12. 12 minus the expected of 10, subtract, and square, and divide by its expected value. Red, the sigma means add. So we add all these together. Using order of operations, remember from high school, please excuse my dear Aunt Sally, parentheses, exponents, multiply, divide, add, subtract. In my parentheses, 8 minus 10 would be negative 2. That has to be squared and divided by 10. So I have 4 divided by 10. Second value, 10 minus 10 would be 0. 0 squared is still 0. 0 divided by 10 would be 0. My last value, 12 minus 10 would be 2. 2 squared divided by 10. Again, I have 4 out of 10. Sigma says add all those together, and I would have 8 divided by 10, or 0.8. Calculated value of chi square would be 0.8. In my comparison for step 4, I would take a curve. Chi-squares are not symmetric, they're skewed right. My critical value on a number line is just shy of 6, 5.991, and that would return my rejection region. However, when I compare what I've just calculated by hand, that is at 0.8, definitely not in the rejection region. Therefore, I will fail to reject the null. I do not think my research shows what I was trying to find out. I think, based on the information I currently have in my sample of 30, the proportion of the automobiles, it's equal for age. A random sample was taken to see if the proportion of car crashes differs by age. Using the data below, test the chi-square statistic for significance. First thing we need are hypotheses. The research hypothesis, HA or H1, is known as the proportion of car crashes differs by age, which would mean then that the alternative to that, the null, would be the proportion of car crashes is the same despite age. When we want to do our actual hypothesis test, we would have to see what the critical value is. Since alpha is not mentioned, we would have to go with the assumed value, the default of 0.05. There are 1, 2, 3, 4 groups, so our degrees of freedom will be the number of groups minus 1, or 3. So now we need to go to our chart. With 3 degrees of freedom and 5% significance, our critical value would be 7.815. Now, to go to step 3, the calculated value, we're missing the expected value, so we'll have to find that. The first thing I need to do is figure out how many people are in this sample. So if I add these numbers together, 66, 39, 25, and 30, I get a total of 160 people. The expected percentage, since I'm thinking that they are proportional, equal by the null, I would take my 100% and divide it between the 4 groups, each group giving 25%. So then when I go for my expected data, I'm going to take my total times the percent. That's the formula for getting the expected data when we're using only 4 groups, 1 column of observed data. So I will take my 160 people for my total times 25%, and I'm going to get 40. Since they're considered equal by the null, they would all be 40. Those numbers will be important for my calculation. Chi-squared equals the addition of observed minus expected, subtract them, then square, then divide by the expected. So according to my observed data, my first piece of information would say 66 minus 40. Subtract it, square, and then divide by the expected value. My second piece of data is 39. That's observed. I'm expecting, if all things are equal as the null, that it would be 40. Square it, divide by 40. The third piece of data is 25 minus the expected 40. Subtract it, square it, and divide by 40. And then finally 30 minus 40. Subtract it, square it, and divide by the 40. Now we're actually going to do the calculations. With our rusty trusty calculator, 66 minus 40 gives us 26. Square it, then divide by the 40. We're going to take 66 minus 40 and get 26. 26 squared, and then divide that by 40. 16.9. 39 minus 40 is 1. 1 divided by 40 is 0.025. 25 minus 40 is 15. 15 squared is 225, divided by 40 is 5.625. Finally, 30 minus 40 is 10. 10 squared is 100, divided by 40 would be 2.5. The sigma in the formula means add, so I'm going to add all those together. My calculated chi-square value is 25.05. So in my picture I want to compare them. My critical value was 7.815. This means that about 5%, the alpha value, is shaded for the rejection region. But my calculated value, I'm going to get this out of the way because I'm going to need some room, is way over here. Definitely in the rejection region. We will, in fact, reject that null. And so our interpretation, there is enough information to show that the proportion of crashes does differ in the population. Or we could say there is a statistically significant difference in the proportion of crashes by age group.